Aloha, Rich Halverson here, and this is ITS388AL, and this is video number 3. And today we're going to cover Chapter 2, cover the important points of Chapter 2. So let me share my screen. Okay, this is we're doing Chapter 2 here. And let's just take a peek at the textbook where we are. This is a pretty important chapter because it explains the register set of the microprocessor. And you have to have the register set in mind whenever you're writing programs. So some of these block diagrams really are not relevant. They are relevant because it's how the architects of the microprocessor sort of arranged everything, and it's interesting to understand, but you're not going to be tested on it specifically. This here is where we start to look at the register set, and there are these things called general purpose registers, and there's some flags which give certain conditions. There are things called segment registers. It's how the microprocessor separates people's programs when there's more than one program running at the same time. There are also, each register can be addressed with different modes, and depending on the size of the operands that you're manipulating. So a single the EAX register, for example, can be used like an AX register, a single AX register, two 16-bit registers, or even 4 8-bit registers. And this is how you refer to or you reference these registers, depending on what operand size you're doing. And there's also these MMX registers, multimedia. For multimedia, they're SIMD instructions, which is single instruction multiple data stream configurations where you can process, say, for example, you have three streams coming in for color, and you're processing chunks of data, set of 3 at a time. And there are these also these floating point registers that when the floating point processor was incorporated into the processor itself, the registers came with it. These are larger in size. It requires more accuracy. 64-bit processors now, there's a 64-bit mode and a 32-bit mode, and so you got to pay attention to that. This chapter later on goes into what the motherboard looks like. That's not really that important for this class. So I'd like to just go through the slides here. Let me also point out there's a quiz, there's a chapter quiz, there's a weekly quiz and a chapter quiz, and the quizzes are true false, as you know, and along the side of the quiz question it says what chapter and what week it belongs in. So you can take as much time as you want to take these quizzes. The multiple choice quizzes, you only get one chance, but take as much time as you want. You can have your textbook open, and so you want to nail down what all these concepts are. And then each chapter has this fill in the blank test. I just call it a test to separate it from, so you're not confused with the true false quiz. But it's a fill in the blank, and so you just have to fill in these questions here. There's 10 of them, and it's the same kind of thing. You can have your textbook open at the time, and you should be able to get in. For these, you get more than one chance. I think you get 3 chances to get all the right answers with the test. All right. So let's page through these slides here. Just make sure I'm doing everything I should be doing. Yes, okay. So chapter 2, this is the architecture. We're going to cover general concepts. The 32-bit processor architecture, the memory management, 64-bit processors and components, the I/O system. General concepts, basic microcomputer design, the instruction execution cycle. It's kind of interesting. It's good to have insight into this so you know why things take longer. Sometimes instructions might take longer than other instructions, how programs run, how data is transferred to and from memory. So this is a basic block diagram. This is pretty accurate. We have something called a data bus here, and that would be 16, well, whether it's 8-bit, 16 bits, or 32 bits. Tell you what, I'm gonna unshare this for a moment, and I'm gonna move my slides over to the computer I can use to write with. Now let me share this again. All right. We have here, let me make this a little bit larger. So we have an 8-bit bus here. Let's see. Let's make this dark blue. So back in the old days when we just had 8-bit microprocessors, or the 8088, which was 16 on the inside and 8 on the outside, the 8 is the size of the data bus. So this can be 8, 16, 32, or 64. And the thing is if it's only an 8-bit data bus, then if we want to transfer 16 bits worth of data, it takes two cycles, or 2 transfers. If you want to transfer 32 bits, it takes 4. If you want to transfer 64 bit, it takes 8. So that's how the size of the bus can slow things down. The data bus can be it's bidirectional, of course. You can send data in, take data out. The address bus is just simply this direction, though, because the address that you want to reference comes out of the central processing unit and lays itself onto the memory, and that determines what is actually going to come out of here or what gets written into here. The I/O devices, which are usually byte transfer or 16-bit transfer for whatever to and from the printer or the network card or the whatever, that looks a lot like memory to the processor. You see, we still have it, we're addressing it, and we're getting data in and out the same way, but there's some special instructions that help make that transfer easier. So let me continue on here. There's a clock inside, and when we refer to the gigahertz of the microprocessor, this is what we're talking about. It's the most granular unit of operation, and it's used to trigger events, and oftentimes it's many clocks to do one particular operation. Like when you're accessing memory, it may take several clocks before the data actually finds itself back in the gates into the processor, and so on. We're talking about delays, and bus delays, and so on. If we go into the 32-bit processor architecture a little bit, this is a meaningless slide. This doesn't make any sense. I don't know. The address bus is. I'm just not even going to look at that one. Okay, reading from memory. Steps. Multiple machine cycles are required to read from memory because it responds much more slowly. So what happens is the address is placed on the address bus, and then a signal on the control bus gets yanked down or yanked up, which says read instead of write. And then it waits a clock cycle for the memory chips to respond. It's got the addresses to propagate into the memory chip, and then the data finds its way out the data bus and on its way back to the processor. And then the data is copied from the data bus into the processor, usually into a register, or always into a register. Uh, Cache memory is, it serves sort of the same purpose, except for this can be, this is like intermediate memory. Because RAM memory can be so slow in these processors. In the beginning it wasn't that way, but now it is. You like to, if there's data that you can access very often, you can put that data in caches, which is memory that's closer to the processor, so it'll take less time to get to it. And so if the cache unit has to be very smart to know what data to actually store in the cache and what data not to bother storing in the cache, because of course the size of the cache is limited. And if there's a cache hit, you're successful. It doesn't take very long. If there's not a cache hit, then you have to wait for the data to come in from the memory. This is how a program runs. Operating system. This is not that important. Modes of operation, execution environment, floating point unit, and processor history. It's not very important. There's the modes of operation. We want to understand these. There's protected mode, which is we use there's a bunch of this can address memory. I think only like 1 megabyte of RAM, or maybe it's I think it might be bigger than that. But there's the processor enforces segmentation, and so there can be many programs in the memory, but each program is limited to accessing data within its own segment, and so that's protected mode. Real address mode is when you are actually emulating the old MS-DOS processors. MS-DOS operating system. And then system memory management mode, which is another mode where if you're worried about power management or you're doing you want added security and so on, that's a third mode. And then this virtual 8086 mode, it's kind of like real address mode, except for you can have a bunch of them. So it's sort of a hybrid of protected mode and real address mode. We will be operating, I think, almost all in just this protected mode. That's the most common, I think. All right, so the basic execution environment, there is addressable memory. There are general purpose registers, which we have to be aware of. There's index and base registers, which we have to be aware of. There are some specialized register uses, which we have to know. There are a bunch of status flags. You know, you just finish an operation. Does the accumulator contain 0 now, or when you did that subtraction, did it end up resulting in a negative number? So on. Was there an overflow? Did you try to add 2 numbers that are too big and it didn't fit in the resulting register? Those status flags are very important there. And then there are some additional registers here to support floating point and memory management. So for addressable memory, a protected mode, I'm sorry, it's 4 gigabytes. That is 2 to the 32 power. That makes sense. 32-bit address space. 2 to the 32 power is about 4 billion. This real address mode on virtual 8086 mode is just 1 megabyte of space, a 20-bit address. That was back in the old days, the old 8086 machines, you know, the 186, 286, and so on. Those were just I think it's just the 80, I think 286. I can't remember that might have gone up by then. But anyway, so these are what the general purpose registers are. When you are writing your programs, you are going to be storing data. You're going to be storing data as you're calculating in these registers. You'll notice that this is A. This is like A, the A register, the B register, the C register, and the D register. So you've got kind of 4 to work with. Okay, and these are 32 bits big. So you can, so in almost all the calculations you're going to be doing, that's plenty. These here are the status flags, and by the way, the E stands for extended. And so these contain all kinds of conditions and stuff for after you do an operation. Certain flags are set or cleared, and then you can jump. You can do tests on them and jump to different you know parts of your code and so on. This is the instruction pointer. This points to the next address in the next program address in your program. So this is pointing into program memory. Whereas up here we have this is the stack pointer. So you know, stacks are used for like when you're calling subroutines and stuff. You want to store the return address on the stack. If you're supporting a higher level language, you want to store your operands on the stack. This is the base pointer, which also points up into the stack area, and of course that's how you would refer to operands on a stack in a conventional programming language. When you're doing string copies or string manipulations, or you're moving data from one place to another, these registers are convenient to use. This is S stands for source, like the source of, you know, like you're copying from a source to a destination. This is destination. These names are just convenient, and these registers are designed to help you do those things. But really, these registers can be used for anything. You can store data. If you're not doing anything with if you're not implementing a higher level language, you might not need the base pointer to point it up into the stack. So you could just use it to store some data if you want to, like if you're doing some calculations normally using these registers. These are segment registers here, and these point to blocks of memory. And this is how it's able to separate programs, where if there's multiple programs running at once. This is the code segment. That's this. I don't know how large these are, but these point to whole segments of memory, and so your code is loaded into a code segment. You've got a stack segment. You've got a data segment, and EFG. I'm not sure what segments those are. Extra segments and so on. That are used, and in that way, and all the instructions. Well, there are certain instructions there are certain instructions that are used to manipulate these registers, but those are usually protected operating system instructions, and all the other instructions that we use to write our programs. We don't really think about what the values are in these registers, because these just point to where these are like base registers. If we're dealing with a stack, the location of the stack is going to be in this register, in the SS register, but it's not like we're going to be manipulating that for any reason. The code segment register, when the operating system loads our program into some place in memory, the operating system is going to say where that code segment is. But as our program executes, we aren't going to really be aware of the value of the code segment. Everything is just going to be relative to the starting of the code segment. All right. So here we're using accessing parts of registers. Let me just so the EAX register is 32 bits, as you can see. And some instructions, though, we're only using the 16-bit, the lowest part. So we may be having some instructions that refer to AX instead of EAX. And we also may have some instructions that refer to AL and AH as opposed to, you know, AX. And so if our operands are 8 bits, like when we're manipulating ASCII characters, we are referring to that register space this way. When we're dealing with 16-bit words, which, you know, are Unicode or whatever, we may refer to them as AX registers. And if we're doing some integer calculations or whatever, we would refer to them with EAX extended. And same with the index and base registers. So you're probably wondering why we even have 16-bit and 8-bit. That has to do with the history of these Intel microprocessors. You know, the first microprocessor in the world was the Intel 4004, and that was just 4 bits. That was just a 4-bit. The buses were 4 bits, so we were just dealing with what they called nibbles. You know, the half of a byte is a nibble. And then we went to Intel expanded and went to an 8-bit bus, and so there was the 8008 and the 8080, and then that was 8 bits, and then they came out with the 8086 and the 8088, and those are 16 bits. But each time they had sort of this backward compatibility thing going on, so they still wanted to be able to run. You may have to do some reassembly, but they still wanted to be able to run the 8-bit programs on the 16-bit processor, and they still wanted to be able to run the 16-bit programs on the 32-bit processor, and you'll see they still want to run the 32-bit programs on the 64-bit processor. So they care about this backward compatibility. You might not be able to run directly, but by just reassembling or recompiling your code, it's very simple. It translates into being able to execute this forward compatibility thing. Backward, there's no backward compatibility, but forward compatibility. All right, let me close this for a moment. So we have index and base registers, some specialized registers. We generally call the EAX register the accumulator. We generally call the ECX register the counter register, and you can easily there's increment instructions and so on, which help with that. You may use the counter register to point off into memory someplace if you're gonna want to move some data around or whatever. The ESP register is a stack pointer. These index registers, source and destination, and the extended frame pointer, that's points into the stack. That's if you're passing parameters between higher level language programs when you're calling methods and so on. And then there are the segments, which I mentioned earlier. The EIP register, that actually points into the code segment. That's the next instruction that's going to be executed in your program. And of course, if you're going to jump to a different place in your program, it's the EIP register that gets written into. There's flags, which can have status and control and so on. These are some of the important flags. There's a carry flag in case you're adding two 8-bit numbers and the result is bigger than an 8-bit number. It's going to there might be a carry flag or an overflow flag. They're similar but not quite the same. There's a sign flag. It's the highest order bit is a 1. It usually represents a negative number. There's a flag where if you do an operation and the result is 0, it sets a flag. It's easy to test for that. There's this auxiliary carry flag, which is a carry between bit 3 and bit 4 of a byte, and that's useful when we're it's useful when, for example, I'm not positive they actually do it this way, but to implement the decimal number type in C#, they probably use this because they probably represent numbers as actual in decimal format. And if they do that, they're going to use 1 byte. 1 byte will hold up to between 0 and 99. And 1 nibble can hold 1 decimal digit. So 1 nibble, of course, is 4 bits, and that can store a number between 0 and 15 or 16. But we're only going to go 0 to 10 or 0 to 9, and then we start over again. So you're actually able to do addition and subtraction and so on, treating where it's decimal, binary coded decimal, and so that's when this auxiliary carry becomes important. And parity just says how many. It says whether or not the sum of the 1 bits in a byte is an even number, and that's useful if you want to detect if there's errors by hardware errors or transmission errors. There are the floating point registers, which are much larger, can store floating point numbers. 80-bit floating point numbers are, you store the exponent, the mantissa and the exponent, and so on. Memory management, this discusses how we keep track of the different addressing modes. This is probably isn't too important in this course, but if you were to go on and be a systems programmer or writing operating systems code or whatever, you really do have to understand these different memory models. Protected mode is up to 4 gigabytes. You notice this is 32 bits. FF, 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 4 bytes. Each program is assigned a memory partition, that's a segment, and it's designed for multitasking. 64-bit processors, that's supporting, even higher accuracy. Addresses, compatibility mode, you can run existing 16 or 32-bit applications. The addresses, there's a 64-bit address space, but we aren't there yet, so we only 48 bits are used so far in practice, but just give it a couple more years and we're going to have, fortunately, have another 16 bits there to address even more space. There's 16 64-bit general purpose registers instead of just 8 as before, so we actually get 8 more. And then there's a 16-bit instruction pointer called the RIP instruction pointer. So these are the 16-bit general purpose registers. We have, if we're doing 32-bit operands, then we still have the regular set that we normally have up to here, but then we also get 8 more. And if we're using 64-bit operands, then it just looks like this. This is components of a microcomputer, motherboard, video output, memory, or outputs. I know there are individuals in this class that know a lot more about this than I do. So you can look through here. This isn't that important for this class, but it's a good idea to understand all this stuff, because when this stuff advances, you're going to know how it's going to affect your assembly language programming. Video, that's what a video card looks like. It's PCI interface looks like. There's different kinds of memory which you should know about. ROM is sort of hard-coded, hardwired on the motherboard, or it's inside chips along with other stuff, and it's fabricated that way. The data is fabricated. It's when they produce the chip, it's the ones and zeros for the memory are burned in. With an EEPROM, you're able to program the ones and zeros later on, and it takes longer to program them, much longer than it takes just to writing memory. But once it's programmed, you can turn the power off and everything and turn the power back on later, and it's all still there. And you can erase them. In the old days, these chips would have a little window on top, and you'd shine an ultraviolet light on there for a half an hour, and it would erase them all. I don't know if that's still how they do it, but it's the idea. Dynamic RAM is it's the most compact. It requires the least amount of space to store a 1 or a 0. It just takes a little capacitor in there to store a 1 or a 0. The problem is that when you store the 1 or the 0, for that matter, it's only able to store it for like a few milliseconds or so, and then it has to be refreshed. By refreshing, you read the data out and you write the data back in again, and that sort of refreshes it, and it's able to store it again for another few milliseconds. Now, a millisecond in computer time is hardly any time at all. I mean, a millisecond is it doesn't happen. We're dealing with nanoseconds, and for data transfer, and a millisecond is like 1,000 times longer, so it's like every 1,000 times it's got to read it out and write it back in again and all that, and so it ends up being a very efficient way. The trade-offs. Static RAM is sort of halfway between ROM and dynamic RAM. Static RAM, once you write it and keep power on it, then it stays. The data stays. So you don't have to refresh it. So you have to keep power on it, but you don't have to refresh it. Video RAM is two-ported. What that means is that there's a data bus going in and a different data bus coming out. And that means that you can write the RAM at the same time you're reading the RAM. So with all this other kind of RAM, the data bus is bidirectional, which means you either use the data bus to write data into the RAM, or you use the data bus to read data out of the RAM. But video RAM is two-ported. Chips have to be bigger, too, because more pins. CMOS is a particular type of RAM, complementary metal oxide semiconductor. With most static RAM, if you're storing it takes power to hold the data. It takes power to hold it. So you're consuming power all the time while it's on. With CMOS, you only use power to switch for the most part. You still need power, but it's like very little power, very little power. So if you're just storing data and you aren't reading or writing it, if you're not writing it, if you're only reading it, or you store it in there and you don't need it for a while, CMOS RAM. So that's why CMOS is low power, because it only consumes power when you're switching from a 1 to a 0, or you're switching from a 0 to a 1. And so that's why CMOS RAM is low power, but that's also why in fast systems, in very fast systems, CMOS consumes a lot of power, because in fast systems you're reading and writing a lot, a lot of reads and writes in a short period of time, and that can consume more power. We have input-output ports, and we have serial input-output, which is just 1 bit, but it can be fast. It's just 1s and 0s, though. Parallel means you have more than one at once. It used to be that you'd interface to a printer with a parallel port. So we still have serial ports and parallel ports. This is the old-time RS-232. This was an old chip that we used to use to implement an RS-232 interface. These are device interfaces for disk drives. They need to be faster. Other kinds of interfaces. Input-output system. Levels of input-output system. There's I/O at level 1, which is assembly. I/O at the operating systems level, and I/O at the high-level language level. This here you're writing to the printer or whatever. This operating system you're writing to probably to ports and so on. Here you're writing bytes to ports and reading bytes from ports. Assembly language program. Assembly language programs can perform input-output at each of the levels. You're either reading and writing directly ports using instructions, or a BIOS function is usually a method. It's in assembly language. It's called a subroutine. That's in the BIOS, and if you want the assembly language program to write something to the screen, you will call a library function in someplace, and it'll take care of that for you. So central processing unit, let's see, I've shown you everything, went through the slides. The complex instruction set, you're going to have to know all the instructions. We haven't really covered any instructions yet. Memory modes. You're going to have to know a little bit about memory modes in this class. Not that much here. What is the real important parts? The register set. The register set's the most important part in this. Yeah, these status flags and these registers. This is the most important diagram, I would say, from this chapter, because you're going to be reading and writing these things all the time. All right, let me stop my sharing here. So that's chapter 2. We've covered chapter 2. So I hope this helped, and thanks for watching.